Hello, hello, hello. Good afternoon, Internet. Welcome. See, I'm all dressed up here for the summer again, right? Got my cap on, ready to go outside after we're done here talking today. Out in the sweltering heat. The sweltering heat of I guess the new normal of summer. I don't know, man, like 30 plus degree weather. Boy, oh boy. Yikes. I mean, what is this? What is this? Like the mainland? Come on. Jeez. It's like 33 outside with the humidex. It's bonkers. Anyway, welcome. Welcome to day 63 of NL Mathman's Math Help Stream. Um, yeah, this is it. This is the final day. This is the final day for season one, I suppose. Unless something, you know, unless something comes up and I end up working other times over the summer, which I mean, there's an outside chance of that, I suppose. But as far as I know, and as far as anyone I know knows, this is the last of them. This is day 63. Yeah, we're gonna be calling it here after the stream today. Um, Maybe you might have thought, hey, what's he gonna do? Is Peter gonna do something special on stream today for the last day? You know what I'm gonna do special for stream today? I'm gonna do physics and math. That's what I'm gonna do. That's special. I mean, I'm wearing a hat that's kind of special, right? I'm gonna take it off now in a minute, probably. Um, yeah, what am I doing for my last day? That's special. Like I said, physics and math, baby. That's how we do it. That's how we roll. We out here doing schoolwork, We out here schmoovin, although schmoovin very slowly. Schmoovin my hand, right? You know. That's how we do. Um, yeah. No, I guess I'm just gonna get into it here now in a second, I suppose. Um, Normally, like I said, normally I would do, say, a bit of a farewell thing, at the last day. But this isn't the last day for a whole lot of my students. A solid third of my students are carrying on and going to a different campus to keep on doing work over the summer. So I'm going to focus mostly today on doing some work for those students because for them, hey, Monday it'll be with a different teacher, but their programs continue. So I'm going to continue introducing topics and talking about topics just as normal. Um, I'm also going to go over some questions for a student that finished a test today, right? So we're gonna start off with those because I mean, you might have pieced together or you might have known firsthand. The way I do this is I do my correcting before the stream or as much of it as I can, and then I write up my examples and save them so students know the correct working, and I talk through it and stuff, and then send out the videos. So we are going to discuss a little bit here now today from activity for Troy in Physics 1104. So, without further ado, I am going to skip on over to that one. Over to my document display. Here we go. Now, see, now the cap. The cap looks the part here, doesn't it? It's a nice cap. I like this one, right? It's outdoors Newfoundland. It's got some nice labels on the side. Look, we got a Yami over here, and we got what's over this side? Steel, I think. No, Husqvarna. Husqvarna's on that side, and Steel's on the back, right? If I had her turned around backwards, as if I was a cool guy. I don't know why you would wear a hat like this though, especially in the summer. I guess to keep the sun off your neck. Yeah, I guess so. Anyway, it's a nice hat. I like that one. I wear that one a lot. But today now, we're going to start off with some Physics 1104. Like I said, as we are out here doing the math, doing the science. So let's see. I've got six questions I'm going to work down through on this guy. So, yeah, a lot of this is actually going to be on graph paper, but we'll start off on this sheet. So, question 3. These ones are a little bit tricky, right? They're trying to trip you up here as normal, right? That's what you do. That's what we do as teachers, right? Which of the following is an example of displacement? Happy last, Peter? Yes. Same to you, Betty Ann. Well, it's not the last day for you, is it? No, you'll be carrying on. Last Peter Day? It's the last Peter Day. That's right. Last day, Peter. Yeah, I know what you mean. Although for you, yeah, you'll be carrying on Monday. And the second thing I'm going to do today is an introduction to your next course. The next course sort of starts off with a recap of several topics that you will have already seen, and then it introduces the quadratic equation, which is extremely useful. So we're going to go over that a little bit. For Troy, then, let's see here. Number 3, which of the following is an example of displacement? Now, this one's a bit of a cheeky one, right? We know, well, what is displacement? Displacement is basically speed, but with a direction, right? No, so that's velocity. Never mind. Velocity is the displacement one here is just going to be a distance with a it's going to be a distance but with a direction, right? So that's going to be c, of course, right? I think I will check again, Troy, before I finish here, just to make sure that the corrections for the test were right too. Sometimes the key gets them mixed up. Like, I guess it's easy when you're going down through a key and making one quickly, right, to jot down the wrong number for some of these. But for 3, C is definitely the right answer there. 1.5 meters right is an example of displacement. B, 20 kilometers an hour east, that one is an example of velocity, right? So for number four then, which of the following is an example of velocity? Well, that's going to be B, right? Because velocity is sort of speed with direction, right? Just to say it really simply. Some of these are going to take a little bit longer, but these first two I'm going to tear down through pretty quick, as we saw. Number 9 is the next one I'm going to do. A car starts at rest and accelerates at 2.0 meters per second in 3 seconds. Its displacement is what? Now, yeah, so here you do actually have enough to answer the question, right? Because it does specify that it accelerates at 2.0 meters per second for 3 seconds. Basically, it should say for 3 seconds, not in 3 seconds. The in 3 seconds part there. I mean, if you said D for this, I might give you the marks for a question like this, because, if it says accelerates at 2.0 meters per second squared for 3 seconds, that would be a bit clearer, I think. But either way, let me grab, didn't have this graph paper ready to go. Okay, so let me grab this, and like I said, we are going to do quite a few of these questions on graph paper today. This is going to be physics 1104 again. I'm going to do question 9 over here. Grab a straight edge. So I think oftentimes in a situation like this, the easiest way to approach doing one of these questions is to graph it out, right? When in doubt, draw it out. That's what I always say, or occasionally say. Either way. So what we've got here is we're told it accelerates. So I'm going to go ahead and do a velocity time graph, right? We're going to have velocity over here, right? This one is going to be time. Time is going to be in seconds. Velocity is going to be in meters per second, right? I'm going to have each block be half. Boy, what the heck is a piece of dirt attached to? 4, 5, and so on, right? And then the velocity, let's just do one per block. 1, 2, 3, 4, 5, 6, 7, 8, 9, and so on, right? So it starts from rest, so we know it starts from over here at 0, 0, and accelerates at 2.0 meters per second for 3 seconds. So for 3 seconds, it goes up by 2 a second. Now, what I'm going to do, the way I've drawn it, it's actually just going to join up like so, right? But don't be fooled. Don't be fooled by the number of blocks it takes up. That's not really the relevant part that we're looking for, right? What we're looking for here is the size of the area underneath said line, right? So what we're going to do now is we're going to join this up down here, right? And like I've explained before, right, what we're looking for to find the displacement is going to be this, right? This blue shaded area over here. This is what we're trying to find. So how are we going to find that area? Well, of course, the area is going to equal a half of the base times the height, because it's a triangle. Or in other words, it's going to be a half, right, of, well, the base is going to be 3 seconds, and the height is going to be 6 meters per second, right? So we're going to end up with 1.5 times 6, or 3 times 3, whichever way you slice it. And that's going to end up with 9 meters. It's going to be your answer, right? And we know it's north because this is velocity in meters per second north. I should be very clear with saying here. So it's going to be 9 meters north as our answer. Okay, so we know that that is going to be option A on the list there, right? And again, it's just sort of a fairly straightforward application of just the geometry stuff. But the really important part, like I'm saying, is to graph out the situation. And I think once you graph out the situation, a lot of these times it'll become really clear what we're doing and why. Right, let me carry on here now. I've got questions. Let's see, I want to do questions 22 and 28. Those are a bit more significant. So let me just scroll on down. Oh, I skipped 22? I did. Okay, got to zoom out a little. A jogger is out for her usual run. She travels north, covering 3 kilometers in 30 minutes. She then turns south for another 6 kilometers in 50 minutes. Calculate the average speed for her run in kilometers an hour and the average velocity for her run in kilometers per hour. Okay, so this is really just a question asking you about the difference between speed and velocity. Right, so let me do, I'll do question 22 down here. This is not a ton of drawing necessary for this one. But of course, the first sort of leg of her movement, when she travels north 3 kilometers. So let me see. Let me put her starting position here. We'll call this her start, right? And she's going to go north 3 kilometers. So this is going to be 3 km in here, right? That's what she does first. Actually, tell you what, I'll use 2 blocks per so we can actually see it a bit better. So that's going to be 3 kilometers north, right? Then she's going to turn and she's going to go south, right? She's going to do a total 180, which does allow you to walk away afterwards, right? So an X box 180. Then she's going to go south for 5 kilometers, or 6 kilometers, sorry, in 50 minutes. So it's going to be this 1, 2, 3, then 4, 5, and 6. Yes. So this is going to be 6 kms. Right? So this is basically the situation that she goes in. Right? And let me write this a touch bigger so we can see it a little better on screen there. So that was 3 kilometers north. All right, that's a bit bigger. New final stream for the semester. Gone from us too soon? Yeah. Well, it was 63 days. 63 days is not a bad amount of work. Right? But yes, we're going to be taking a bit of a break. But it's entirely possible that NL Math Man will return, at the same math time and the same math channel in September after Labor Day. It's possible. And there isn't, like I said, there's an outside chance that I'll be doing more this summer. But I don't know. Like I said, I don't know, and I don't know anybody else who knows. But we'll see. We'll see how that goes down. For 22A over here, right, the average speed for her run in kilometers per hour. Well, speed, of course, is just distance divided by time, right? Right, so her speed is going to be the 3 kilometers that she went north plus, I'm gonna alternate colors a bunch here, the 6 that she went south, right? And how much time did she take? Well, let's see, 30 minutes and then 50 minutes. right? So let's do, well, that'll end up with kilometers per minute. So how's about I do kilometers per hour, right? Yes, we're asking for kilometers per hour. Okay, so it's 30 minutes out of 60, right? 30 out of 60 is how many hours that is. Plus, then this one is going to be 50 out of 60. Is how many hours that one took, right? Got started with calculus on my afternoon walk today. Well, excellent. Doing calculus on a walk, that's great timing. Yeah, absolutely. Do some get to do some integrals. You were finding area under curves during a walk. I mean, that makes sense, right? Like this is the kind of stuff we're showing today. This is area under a straight line, which is, you don't really need calculus to figure that out, though you could. You could use calculus to figure out the area under a straight line, but it's sort of like, you know, I don't know. It's kind of like driving a nail with a jackhammer. Started with differentiation. Ah, excellent. Yes, that is where you would normally begin. That's right. Yeah. So then the speed is going to be 9 or 9 km over 80 over 60 hours, right? 80 over 60 is just going to be 1 1/3. But all we're going to do now is just divide, right? 80 over 60 is 1.33, of course. And then 9 divided by that number is going to be 6.75. So that's going to be, now we were told 6.0, but 50. Now, Troy, you were right. You were right on the one that you looked at, that you solved this to 1 decimal place. You called this 7, right? Now, the guide does call this one 6.8 because it says that 30 and 50, they treated those as having 2 sig figs. But I think to be very precise, Troy, you are right that we would round it to 1 sig fig because 30 and 50, they would need to be written as 3.0 times 10 to the 1 if we wanted to represent that number as having 2 sig figs, right? I know it's, right, like, that's a bit odd, but you're totally right that is the way we do it. So 6.75 kmh or 7 kmh to 1 sig fig, right? So that is how we would do part A. The reason I wanted to show this one on stream was because I wanted to show about part B over here, right? So for part B, we are actually going to have to use the displacement rather than the distance, right? Because B is looking for the velocity for her run, and we know that velocity equals displacement over time, right? And what's the displacement here? Well, I'm going to search around for my green pen. Here it is. Okay, so our displacement then was going to be just from the start to the finish, right? So displacement is just going to be 3 kilometers south, right? Because that's where she ends up in the end. She ends up 3 kilometers south of where she started. So the velocity, then, we know is just going to be this 3 km displacement divided by our time, which is still going to be 4 over 3, right? 80 over 60 is the same as 4 over 3. I'm just simplifying it a touch here. So then the velocity, 3 times 4 over 3 is going to be 9 over 4. 3 divided by 4 over 3, rather. 2.25. 2.25 kilometers per hour, or it equals 2 km per hour to 1 sig fig. Right? So that is how we're going to go about doing question 22. The main thing there is just to know the difference between velocity and speed, right? So her velocity relies on her displacement, which is right? There's 3 kilometers from where she started to where she finished. Sort of, you can think of it as, like I said, the distance between where you start and where you end is your displacement. Displacement is distance from the straight line. Yeah. I mean, it's kind of a straight line basically from where you start to where you end. Yes. Whereas distance is like the total amount of distance that you covered to get where you were going, right? So if you turn or something like that, that will obviously affect your distance, but it might not affect your displacement, kind of, if you double back on yourself. And there was one more that I wanted to do on this topic, and I think I am going to need the graph paper to do it. Yes, 28 down here. A cat is accelerating. Boy, a cat accelerates constantly from 2 meters per second west to 7 meters per second west in 3.4 seconds. Find the displacement of the cat during this 3.4 second period. Did they maybe mean car, right? Because 7 meters per second, I mean, that's 25 kilometers an hour. I mean, I guess a cat can move that fast, like for short bursts, I suppose. That's pretty quick, right? It's a fair pace for that kitty. It's a nice kitty, right? Not gonna use too many of Direct Bubbles quotes because then I'll lose my G rating. I think we've already established in an earlier stream that my rating would be more PG, right? So I get 1 F-bomb per stream. So I could. Maybe it's a cat on a scooter? That's true. Yeah, it could be. That would be true, right? Or maybe it's Garfield like sprinting after some lasagna, right? Because he's pretty lackadaisical most of the time, but I bet when there's lasagna in play, he can accelerate pretty quickly. Or when he's got to kick Odie off the table. Okay, so 2 meters per second, 7 meters per second. Right, so we need velocity over here. Velocity in meters per second west is going to be on this side over here. This one down here is going to be, of course, time. Oh, right, and I should be always putting my arrows on those ones to be completely precise. Always got to be completely precise. So it goes from 2 meters per second to 7 meters per second in 3.4 seconds. Right? So I'll do 1, 2, 3. So 3.4 is going to be about here or so. Right? And then it's going to, let's see, how fast does it go? It goes from 2 to 7. So 2, 4, 6, 8. So it starts off at 2, and by 3.4, it's up to 7. So let me just graph what that's going to look like. There we go. I'll draw my dotted line downward. All right, so it's going to be 3.4. I'll just jot that one in there, like so. Right? So now what are we finding out? Well, we're going to be finding the area underneath, right? Because we're looking for the displacement. And right, displacement is the area underneath a graph of velocity and time, right? And it makes sense, right? Because to get the area under a graph like this, we had to take one dimension and multiply it by the other. And we know that meters per second times second, the seconds cancel, and we're left with a value of meters in the end, right? But of course now, this is a compound shape, right? Which is a wonderful topic that we went over in previous courses. But we've got 2 different shapes at play here, right? We've got our triangle, which is going to be the blue area, the blue shaded area over here. Right? We got that guy. And then we've got a rectangle down below it, which is going to be said green shaded area here. Right? So we've just got to take those 2 areas, now figure out both of them, and then add them together is going to give us the area under the curve here, or the area under the line. Right? Well, we know the area of a triangle, right, is a half the base times the height. So the area of the triangle is going to be a half times, so the base is going to be from here to here, 3.4. So 3.4 seconds. That's going to be times the height. The height goes from 2 to 7, like we were told. So the height is going to be 5 meters per second. Like so. All right, so go through and figure this one out. The area of the triangle is going to be 3.4 times 5, divide by 2, 8.5. So we'll call that 8.5. I think we can call it 0.5, right? Because we're told it's, 2.0 to 7.0. So this is going to be 5.0. So it does indeed, we do have two sig figs here, and an exact quantity here, right? This 1 over 2 is not a measured quantity, so we don't need to count that as one sig fig or anything. So this is indeed 8.5 meters for our, for the triangle. And the area of a rectangle is, of course, just length times width. Right? So here now our length is going to be 3.4 again. And then our width, or the height of that, is going to be, it's just going to be 2. Right? 3.4 times 2 is going to be 6.8 meters. Right? Oh, I should have written my units in here again. But yeah, 3.4 seconds times 2 meters per second. So to be very clear, and partly because this is a physics course, we always like to include our units. Like I said before, right, including the units is a really good way of making sure that you're doing the questions correctly, because if your units cancel out to give you the correct value, you know that what you're doing is what you need to. So your area total is going to be, of course, 8.5 plus 6.8, which is going to be, well, if it was 8.5 plus 7, that'd be 15.5. So this is going to be 15.3 meters. So we know then that the total distance that this cat travels with its constant acceleration from 2 meters per second to 7 meters per second west, right, over 3.4 seconds, the displacement is going to be 15.3 meters, and it's still west, because we were told over on the side that this is all velocity going to the west. Okay, so, oh, there was one other question. Yes, there was one other question I skipped over. I skipped over that because I had it written down differently. I did want to talk about question 10 as well. Right, yes, question 10, okay. This is out of order, but it's fine because this is still on the same sort of topic here. Question 10 is that a car slows down from 35 meters per second to 12 meters per second in 15 seconds. Yes, it's the exact same type of question. So let's do that one as well, and then that will be all the ones I needed to get to, Troy, for your activity. And I guess I can dismiss you for the summer, right? Boy, what a world we live in. Okay, 35 meters per second to 12 meters per second in 15 seconds. So let's make this graph relatively big. So I'm going to have each of these 0, 5, 10, and 15. This is going to be time in seconds. And we've got to go from 35 to 12. We've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Let's do 13, 14 blocks here, right? That way this can be 5, 10, 15, 20, 25, 30, and 35. And this is going to be velocity in, meters per second south. Okay. I just wanted to, because you asked about this one earlier, I did want to show how we're going to go about doing this one, right? So in 15 seconds, it slows down from 35 to 12. So it starts off here at 35 at 0. After 15 seconds, it's down to 12. So 12 is going to be about here. So it's going to slow down rather steeply on this graph anyway, like so. Okay? And it's asking for the displacement during this acceleration. So going to use a dotted line here because it doesn't, obviously the car doesn't exactly stop at this point. If it went from 12 meters per second to 0 meters per second instantaneously, like the driver will be dead, right? Like, I mean, instantaneously would be an infinite amount of g-force. Even in like, it was always going to be a given, it's always going to be a non-zero amount of time. If it was a zero amount of time, you'd have an infinitely large g-force, and the person would just sort of cease to exist. They'd be like pushed out of reality or something. Anyway, some nonsensical rambling, but you'll see that kind of stuff later, like acceleration that happens very quickly and how fast the forces increase when acceleration does indeed happen that fast, right? So again, we're going to have a blue area. Oh, am I actually running out of this blue pen too? Have I killed another pen? I'm getting close. Look, it's not coming out super dark this time. Okay, so we're going to have that blue section, right? And then we're going to have this green section. That one and that one. Right, and we're just going to have to add these guys together, just the same as we did for the previous one. Right, so we know again, right, that the area of a triangle is a half base times height. So here, area of the triangle is going to be a half. The base is going to be from 0 to 15. Then what's the height going to be? Well, it's going to be from 35 up here down to 12 down here, right? So, of course, 35 minus 12 is going to be 23. So the area of the triangle is going to be 15 times 23 divided by 2, 172.5. 172.5. It is worth knowing now that it is going down, right? The car is slowing down, but its displacement though is still going to carry on. It's still carrying on to the south, right? It is decelerating here, right? But it's still traveling south. It's not traveling north yet, right? So our displacement here that results is still going to be positive in this case because the displacement is, you can think of it, right? Like it's driving southward and it's slowing down, but it's still driving south, right? So because our velocity in meters, it says south is considered to be our positive quantity here, our displacement is still going to be a positive amount. And then our area of the rectangle is, of course, just going to be length times width, which is going to be, I'm not going to bother to do it quite so much for this one, but it's still going to be 15. Oh, right. I am going to keep in. And keep putting in my units. 15s times, now over here it's going to be 12 meters per second, like so. 15 times 12 is going to be 180. That's right. Yeah. That's going to be 180 meters. This one was 72.5 meters. So then the area total is just going to be 172.5 meters plus 180 meters. Well, this one's not really 172.5, is it? No, it's not. That one should be, I should have written that as 173 meters because it is indeed, we do have to follow significant figures here, right? Because we were told, because this was 35.0 and 12.0, so there should be 3 SF here, right? So this should be 173 plus 180, which is going to be 353 meters. And like I said, it is still in the positive direction because even though the vehicle is slowing down, it is still traveling toward the south. So it's going to be positive 353 or 353 meters south, like so. Personally, I would prefer it if they wrote the answer like this with the south after it. That would maybe make it a bit more unambiguous. But clearly here they were trying to trip you up a little bit between if it would be negative or positive. The truth is that it would be positive, right? Because like I said, this vehicle is still driving to the south even though they're slowing down. Okay? So, Troy, that is, yes, that will be all that I'm going to cover for your Physics 1104. Hope that was useful for you there. Skip on back over to the intro. This is the only picture. The only picture now that I've used twice has been this one, and I mean I think it's evident. It's evident why. This is a quality one, obviously, right? This is about as good as it gets. About as good as it gets for photography. At least photographs with me in them. It's about as good as it gets. That's what I'm saying. Quadratic equations and factoring. I'm going to do a bit of that one next. That'll be for Betty Ann's next course that she's just getting started on. And Betty Ann, you will be, of course, doing work with the teachers from ChemMount as of Monday, I imagine. I don't know what exact setup they have, but they will have something fairly comparable. I believe you'll be downloading, installing, and using Skype for Business. But yeah, I mean, they'll talk you through all that, I imagine. Let me skip on back over now to my document display. Here we go. So this section, this course, is on quadratic equation first, or just quadratics in general. It's great time to introduce that one because it carries on. Quadratic equations and factoring, yes. My favorite topics, great. It's an important one, yeah. It's a big deal one, and we're going to use the best part, the absolute best part of quadratic equations and factoring today, which is the quadratic formula. There's an old YouTube video, right, of some guy singing a song about the quadratic formula. I should look that up sometime so I can link it. I'm going to skip down through some of this because, Betty Ann, you may recall doing, this was in the course that you just did, solving quadratic equations by graphing. And I take a little bit of exception to the way that your book tells you to do it, because it tells you just to find the y-intercept and the vertex. And yes, indeed, you can graph it from that, but it gets pretty hard. It gets pretty hard to graph it with just the y-intercept and the vertex, right? Because look at this graph. Look at this one that they told you to graph with the y-intercept and vertex. Let me keep zooming in. You see how close they are? Right? Like, how are you supposed to extrapolate this whole curve just from knowing this point and this point half a block away from it? My God. Like, that's really, really foolishly difficult. For my money, if you were going to solve one of these ones, graph one of these, the best way to do it is to find the vertex and then to find the roots. So this guy and this guy and this one. How do we find the roots? Well, we gotta factorize, right? That's how I was always taught in school. I wasn't taught to find this part, the x-intercept. I was taught to find the vertex, which is this guy, and then the roots, which are those ones. And the way we find the root is we, of course, set y equal to 0 and we solve. Right? And how do we go about setting y equal to 0 and solving? Well, sometimes it's easy, because sometimes we can use our factoring shortcuts, and we can tear on through it, and, difference of two squares, or, and which is what we get into in 1.2 here. They talk about review of factoring, and they talk you through how to solve these with factoring. Now, the problem is, factoring only works in situations where your math teacher have set it up to work, basically. Right? Factoring is not something that will always work. And so if you're just like, say you've generated a quadratic, never taught anything at school, oh, rip. Get some F's in chat for Slayer Darth's education. Yeah, I mean, when we're taught factoring like this in school, never taught how to graph is something I need to brush up on right now. Well, good, yeah, that's what I'm here for, brushing up on schoolwork, absolutely. So when we're solving quadratics by factoring, generally the quadratic is set up to work that way, right? I don't want to really say in the real world, but in statistical analysis or something like that, you do sometimes use quadratics to model certain equations or model like a set of data. Like sometimes your line of best fit will be most accurate to be a quadratic. But then if you're sort of working backwards, right? If you've got a set of data and you're saying, hey, this data looks roughly quadratic, let's model it as a quadratic and see what we get. It's never going to factor evenly, like basically never. Like one in 100,000 times maybe it'll factor like one of these guys do. It's just not gonna work out nice and smoothly and evenly like that. But you know what works every single time? What works every time, no matter what the question is? Well, it's this one. Quadratic formula right here, 1.3. So this is what I'm going to start talking about. because this is the real meat of what you're getting onto in this next course, is the quadratic formula. And then to use the quadratic formula, we're not going to use like the intercept form or anything like that, or the vertex form of the quadratic. We're going to use the good old-fashioned, abx plus, no, sorry, ax squared plus bx plus c equals 0. We're going to use this, or y equals that. Anyway, to stop rambling and get onto it now, it's going to be Math 2101C, Unit 1, right? So if we have ax squared, so y equals ax squared plus bx plus c, we can find the roots by using the quadratic formula, which is this monstrosity on the page over here to the side. But that is one thing that you're going to be given this one on your tests and stuff like that. But you might end up remembering this guy just from the fact that you'll be writing it out so many times. And it is going to be x equals negative b plus or minus the square root of b squared minus 4ac all over 2a. And those give you the two roots. All right, have a good tip for factoring. If the middle term, the coefficient of x in the quadratic is odd, there must be an odd and even number in the brackets. Yeah, that's true. That's a good point. For some of the time, though, we won't end up with such even numbers for factoring. But you're right, there are a lot of really useful ways to move quickly through them when they're set up so that we can, basically, right? But once we have this guy, this equation over here, we can use this to find the roots of any quadratic, even with like, and a lot of them will have, long decimals and stuff like that, or fractions that don't necessarily work out evenly, but it'll always find us the roots. And we see this plus or minus over here. This plus or minus is important because this is what gives us the two roots, right? So once we figure out the radicand here, or the part that's under the radical, then we're going to add or subtract that. So it sort of bifurcates, it sort of goes off into two sections, and then we can find our two separate roots. Right? So here is one example of going down through it. I am going to, so if you're finding the exact one, you would leave it like this. But I'm going to go ahead and I'm going to do a few of the ones from your textbook here now. So it's going to be page, what is this, 419. Yeah, here we go. Here we go. So Betty Ann, this is a really useful page for you for your next unit. So the roots of a quadratic equation in the form ax squared plus bx plus c equals 0, where a does not equal 0, well, of course, because that makes it a quadratic, right? If a equals 0, it would be a straight line then, so we don't even really need to concern ourselves with that. Can be determined by using the quadratic formula this, which is the thing I just wrote out. The quadratic formula can be used to solve any quadratic, even if the equation is not factorable. That's right. See, this is what I'm talking about. If I had to pick one method to teach students, like say in the general program, where you don't necessarily beat all these different methods of factoring to death, I kind of just teach this one, because you might as well start with the one that's always going to work, right? If the radicand in the quadratic formula simplifies to a perfect square, then it could be solved by factoring. Yes. So if this one, if b squared minus 4ac, if that makes a perfect square number, which is to say this radicand works out to be an even number without a decimal or anything like that, then you could have factored, right? But at that point, you've already got this one done, so why bother going back and factoring? I don't understand. Anyway, if the radicand simplifies to a negative number, there is no real solution. Right? What does it mean for there to be no real solution? Well, if there's no real solution, it looks kind of like this. You see this graph up here, this one? This is an example of a parabola or a quadratic that doesn't cross the x-axis. Because see, the x-axis goes along here, and this one doesn't cross it. In those cases, there won't be any roots. But that's what, in these cases, you will get this number here to work out to be, this b squared minus 4ac will be negative, and that will indicate to you that the quadratic doesn't cross the x-axis at any point. If this works out to be exactly 0, then it means that the vertex is on the x-axis, which is to say it only crosses the x-axis at one point, right? Or if this works out to be a positive number, then it has two roots, right? So I'll write that. Oh yeah, I'll write this out just instead of just saying it out loud. If b squared minus 4ac is greater than 0, has two roots, or crosses the x-axis, if b squared minus 4ac equals 0, quadratic has one root, the vertex is on the x-axis, or if b squared minus 4ac is less than 0, quadratic has 0 roots, I guess I could have said that more elegantly. The quadratic is entirely above or below the x-axis, or in other words, the quadratic doesn't cross the x-axis, right? So those are the three situations here, and you can determine a fair bit about the quadratic simply by figuring out this part first, right? But even just looking at this equation, right, following the order of operations, right, the is bedmass, of course, with exponents. Exponents are the same as radicals, right? Because like I said before, a radical is just a fractional exponent, or it's an exponent of 1 over 2 here. So you have to resolve what's in here first before doing the rest of the equation. And when you do that part, it will tell you the number of roots that the quadratic has. Okay, so let's go down here, because your book asks you to do questions 1. Let's see, 1, 2, 4, and 6. I'll do some of those. I might not do the entirety of 1, 2, 4, and 6. Let's do a few of them. It's going to be page 119, 419. Now, your book, for your guide, for whatever reason, tells you not to graph it. I'm going to go ahead and graph it. I'm going to go ahead and let's bring up Desmos here now in a second, and then I'll graph a few of these ones just so we can see what's going on. Right? For 1a, we've got x squared plus 7x minus 5 equals 0. Now, the thing is here, we might be able to solve this one by factoring, right? Well, we can say, what two numbers add to give us negative, or multiply to give us negative 5, and add to give us a positive 7. Right? I don't honestly know. But you know what we're going to do? We are going to go over here, and we're going to say our a equals 1, our b equals 7, and our c equals negative 5. It's important to call it negative 5, right? Because we keep the sign in front of it with it. And then we're going to go ahead and do our quadratic equation. Negative b plus or minus the square root of b squared minus 4ac all over 2a. So our roots of this one is going to be negative b, which is a negative 7, plus or minus the square root of 7 squared minus 4 times 1 times negative 5, divided by 2 times 1. So then x is going to equal negative 7 plus or minus the root of 49 plus 20 divided by 2. X is going to be negative 7 plus or minus root 69. Nice. Over. That's one of the stupider Reddit jokes. Like at least 420, right? That's a I don't know. Actually, they're both equally juvenile, aren't they? Root 69, 8.3. I'll call that 8.31. So it's negative 7 plus or minus 8.31 over 2. Right? So now, like I said before, now is when it sort of splits off into 2, right? Because I now have x equals negative 7 plus 8.31 over 2, and x equals negative 7 minus 8.31 over 2. Right? And this is going to give us both of our roots. So x is going to be 1.31 over 2, or x is going to be negative 15.31 over 2. So x is going to be 0.31 over 2 is going to be 0.655, or x equals negative 7.67. Right? So those are going to be our roots for this equation. Now I got to tell you, I wouldn't have gotten that from factoring. I would not have been able to factor. I mean, this is almost 2/3, and this is almost, negative 7 and 2/3. I wouldn't have gotten that. Wouldn't have gotten adding those two guys together to get a positive 7 and and then multiplying them together to get a negative 5. But you know what? That is roughly how it goes down, right? But let's, like I said, let me switch on over here. Let's go on over to my Chrome window. That'll pop up in a second. Here we go. So our equation that we had, as you'll recall, was x squared. Oh, let me turn off my caps lock. X squared plus, what was it? 7x minus 5 equals 0. Okay? And what are our roots for that? Negative 7.653. Okay, that's pretty close to what I got. It was a little bit rounded, so it was a little bit off. And this one here is 0.653. Hey, there we go, right? So that is what I found. It's a little bit different because I did, as you recall, I did round the decimal, the root rather, right? If we zoom out then, we'll see a bit more clearly what our, boy, that parabola doesn't end for a while, huh? But there is our graph with the roots that we expected to see. All right, sorry. Yeah, that's the reason. Yeah, don't mind me. Don't mind me. You don't actually put in the equals 0 here to find the to make the graph come up correctly. I would put in the equals y. Yes. Okay, so that was my mistake. So this is what the graph should look like. But here, as you will see, we do still have, that's the root that we found. That is the correct one. And that is the root that we found. That's the correct one as well. Right? And then, like I said before, the way I was always taught to graph these ones in school was to find those two roots, like what we just did, and then to find the vertex as well, right? And remember, your vertex is negative b over your 2a to find the x-coordinate of your vertex, and then you're going to plug that x-coordinate into your formula to find the y-coordinate of your vertex. But that was one of the major topics for your last unit, so I'm not gonna spend too much time on rehashing that guy. Okay. Yeah, these ones take up a bit of space. But let's do a few more. Let's do a few more of these. Let's do some with a bit more significant numbers involved. So let's do, I don't know, let's do 1b. Right? So in 1b, we have 8x squared plus 35x plus 12 equals 0. Now for graphing them, right, like I said, we don't put in the equals 0, but we put in y equals when we were putting them in a graph. But anyway, so our quadratic equation then is going to be x equals negative b plus or minus the square root of b squared minus 4ac all over 2a. And here now, I'm going to go ahead and fill them in. Now, b we can see is 35 because these ones are in order, right? B is always the coefficient on the linear term. It's going to be a negative 35. This is going to be a plus or minus. It's going to be a root of 35 squared, so it's going to be a fairly big number, minus 4 times a, which is 8, and times c, which is 12. Fill all those guys in there. Divided by 2a, so divided by 2 times 8. All right, so x is going to then equal 35 squared. I do not know that one off the top of my head. 1225. Negative 35 plus or minus the root of 1225, subtract 32 times 12, 384. Yeah, I should have got that because that's 320 plus 64. Divide by 16. X is going to equal negative 35 plus or minus the root of 1225 minus 384, root of 841 over 16. And this now, like before, right, figuring out this radical, or rounding it to a decimal value, this is where the difference between our answers and the answers that, say, Desmos would give, this is where it's introduced, right? And just for our own sake, our own sanity, we're not going to try to reduce this down to a simplified radical, not unless you're told specifically to do it. And if you're told specifically to do it, it's probably going to work out reasonably evenly. But here I'm just going to go ahead and mash the square root button for that answer. Oh, well, that one worked out exactly evenly. 29. Look at that. Ah, make a liar out of me. So this one now, because that worked out to be an exact number, we know we could have factored this one, right? So we could, from the start, have saved ourselves from doing all this, and we could have factored it. But, I mean, I don't know about you, but when I glanced at 1b, my first thought was not, hey, this could be factored, right? So, you know, we found out going through that we could have, but guess what? We didn't need to, because at this point now we're practically done, right? Because now we've got x equals negative 35 plus 29 over 16, and x equals negative 35 minus 29 over 16. So we've got two separate situations going on here now. Negative 35 plus 29 is going to be a negative 6 over 16. And then x over here is going to be a negative 64 over 16. Yeah, that's right. Negative 64 over 16. So that one's easy. That one's just going to be a negative 4. And this one, that one's going to be x equals negative 0.375. Okay, so let's let's pop over to Desmos then. Let's pop over and let's plug this guy in, and let's see if we get that answer. Right, go back on over to my Chrome tab. Here we are. So let's plug it in. So our question was 8x squared plus 35x plus 12. And I'll put in the equals y. Let's disable that other one. So here's our quadratic. Here's the vertex of it. We didn't find that, but look at it. Let's look at our roots. Our roots appear to be, oh, come on. There we go. See, if you have the line selected over here, then it comes up with these very handy points on it, which show you the roots just right there, right? So our very handy points are negative 40. Hey, look, we found that one. And then negative 3.750. Right, we got there. So those are the roots of the equation, and we found them using the quadratic formula. Good old-fashioned, old trusty, trustworthy, reliable, reliable, right? The quadratic equation. Okay, so Betty Ann, I think that was that should hopefully be a decent introduction then to using the quadratic formula. Now that I look at them, I think going down through some of these ones is really just repeating myself. A lot of these are very similar, right? Solve it again, and then solve it again. State the solutions as exact values. It's all just this same thing, right? And really, it's just getting used to this formula, and then sort of the other tricky point, I guess. The two other things to really remember is what it means to have either a positive 0 or negative value under this radicand here, or under this radical, or for the radicand, and then what to do when you get down to this plus or minus. But all you got to do is factor off, sort of fraction off, I guess, split off. Boy, I'm using all kinds of math terms to mean something other than what they actually mean. Split off and do a plus here and a minus here. That's really all there is to that. Okay? So we look back over to my intro screen here. We see that I am going to get onto a bit of an inductive and deductive reasoning intro. Now, Emily, this is for your course. I've introduced this topic quite a few times, especially because this one is really odd compared to some of the other topics that we do. I will, when I send you this video, I will also link you some of those other ones. So if you want to see a bit more discussion of this, you can watch those videos as well. But I did want to mention it live here today, fresh as well. But I will try to take a little bit of a different look at it. Oh, hold on there, Twitch chat. I am having a phone call coming in. Now, if this is one of those scammers, I'm going to be relatively annoyed. That's a robocall saying they were calling me from the legal department of Service Canada, involving enforcement, and they're going to have me arrested if I don't comply. I know the rest of it because I've heard that scam before. Let me tell you something, Twitch. Service Canada is never going to call you on a phone. Never, ever. No, they will mail you. They will send you a physical piece of mail. Anyway, this is the robocall from Service Canada. Boy, oh boy. Anyway, jeez. All right, Emily, yes. Now I'm going to get on to talking about inductive and deductive reasoning, and I will endeavor to make it a little bit different than what I have talked about before, just so you get a bit of a different take on it. This is going to be your unit over here. Yeah, like I said, it's quite a bit different than the other math that you will have seen so far. And all you have left to do are these math courses, and this is the only one you've got left, so yeah, we're just going to have to power on through, huh? Right? Basically, inductive reasoning is reasoning through pattern, and deductive reasoning is reasoning through a proof, or something that always happens. I'm not going to go through and write this out right now because, like I said, in the other videos I link you, I will discuss that stuff in some painstaking detail, I think. Right? But I am going to show you some questions from the mid-chapter review here. We're going to talk a little bit about these, and we're going to see a few things that a few examples of the ways that we can use inductive or deductive reasoning, I guess, right? So if we zoom in here, I did talk about this one already as well. A medicine wheel consists of a cairn of stones surrounded by a circle of rocks, the line of rocks extending from the center to the circle. It's a lonely cairn of stones. You know, but one more time I will seek the Northwest Passage, as Stan Rogers tells us. The Moose Mountain medicine wheel. That wouldn't be anywhere near the Northwest Passage, right? That's the West Coast, I believe, right? This is First Nations in BC, I think they're talking about. Is a sacred site created by First Nations people more than 2,000 years ago. Its exact purpose is not known. Make a conjecture about the purpose or usage of the medicine wheel. Now, I did talk about this one previously as well, but this is just to show you that when they come to talk about conjectures, it is every bit as easy as it appears. A conjecture is simply just a theory, right? So a conjecture about this medicine wheel, they use it as a sundial. They use it as a calendar. There we go. Those are two different conjectures, right? I'm now done the question. That's all there is to it. I know sometimes you get to a question like this and it seems, hey, there's got to be more to it than just that, right? That can't be just that easy. It is. It is exactly just that easy. So all you're doing here is a conjecture is really just making a guess, honestly. It's making a guess about something that can be proved right or wrong through various means. A counterexample, which you will see, is anything that disproves a conjecture. For example, So a conjecture is a theory about something, or a theory or statement or claim, kind of, right? So for example, all animals with four legs are mammals. That's a conjecture, right? So a counterexample, right? So a counterexample is an example that disproves a conjecture. For example, crocodiles have four legs and are not mammals. Done, right? Now this conjecture up here is disproved. That's all it is. It is really just that simple. That a conjecture is just a theory or a statement about something, and a counterexample is just one. You just need one counterexample, and the conjecture is disproven, right? Um, yeah, I guess I will. I'll make a liar of myself, and I will go through and write out these definitions. So inductive reasoning. So inductive reasoning is drawing a conjecture based on a pattern. And by drawing, I mean like coming up with. I don't necessarily mean drawing in the sense that you draw a picture, right? So inductive reasoning is creating a conjecture based on a pattern. So when we look at question 2 here, evaluate the following squares, 67 squared, right? So to show inductive reasoning, let's do page, like I said, this is page, what is this? 35. Question 2, right? So 67 squared equals 4489, right? 667 squared, 444889. Oh, 666, 6,667 squared is going to equal, what do we think that's going to be? 444889, right? What do we think this one's going to be? I'm probably not going to have enough room to write this one down. Let's see, 4 sixes and a 7. Square those guys. It's going to be 5 fours, 4 eights, and a 9. Right? So this is a pattern that we're seeing. We see how the number changes. So make a conjecture about the 25th. So my conjecture so the first number has 2 fours and 1 8. The next one has 3 fours and 2 eights. The second number. The third number, 4 fours and then 3 eights. Yes, it was 4 fours and 3 eights. So I'm going to say it's going to have 26 fours and 25 eights and 1 9. That is going to be my conjecture. If I went and plugged that guy into the calculator, I'm not actually going to get that number. It's way too big for the calculator to represent in any way um, other than scientific notation. So it's going to round it, right? Let me show you. Actually, you know what? I can't. I can't really, because it's going to be 25. Never mind. I'm not going to type in 25 sixes. All right, I'll save myself some time here. But so inductive reasoning, all that is drawing a conjecture based on a pattern. So deductive reasoning is making a universal conclusion based on algebraic proofs. Now, Emily, this is going to be the deductive reasoning part is actually when this course is going to start feeling like it's really a math course. Up until this point, it's going to feel a little bit silly up until this point, perhaps, right? But I'll show you here now an example of deductive reasoning, just to help you get started. So let's say we're going to look at page 35 number. Now I've done a lot of these before. Let's do 8. Let's do 8A. Right? I've done a lot of these before, so in the videos that I will send you after, you're going to see quite a few of these ones covered. Quite a few of these ones at the same page. So for 8A, then so they want us to use inductive reasoning first. Right? So inductive. I'm going to pick a number. I'm going to pick a number. Say I'm going to pick the number 4. Right? So then I'm going to add 3. 4 plus 3 equals 7. Right? And then I'm going to multiply by 2. 7 times 2 equals 14. Right? And then I'm going to add 4. 14 plus 4 equals 18. Right? Then I'm going to divide by 2. 18 divided by 2 equals 9. Or I'm going to use the over, not the divide by. Subtract the number you started with. 9 minus 4 equals 5. What is the result? 5. Let's try it again to keep doing inductive. Right? Because inductive reasoning, we need to find a pattern. So just doing it once, very technically, doing it once is not enough for inductive reasoning. So let's pick, I don't know, let's pick the number, let's just pick 7. I don't know, whatever. All right, tell you what, I'm going to make it real tough. Let's do -7. Yeah, let's do something real weird. So -7 plus 3 is going to be a -4. -4 times 2 is going to be a -8. -8 plus 4 is going to be a -4. -4 divided by 2 is going to be a -2. -2 minus -7 is going to be a +5. Oh my God, it did it. It did it. It got back to a 5, even though we tried to throw it for a curve and put a negative in there, right? But now, what's the deductive reasoning? How are we going to show deductive reasoning here? Well, like I said, we're going to use algebra. We're going to use, it's making a universal conclusion based on algebraic proofs. So I'm not going to pick a specific number. I'm going to pick any number. I'm going to pick x, right? Because x can just be any number, of course. We're used to that. That's what algebra is. So the next step is going to be x plus 3, right? Because we've now added 3. So now we're going to multiply this by 2. We're going to be left with 3 outside of x plus 3, or we can call that 2x plus 6. Right? So now we've multiplied by 2. Now we're going to add 4. 2x plus 6 plus 4 is going to be 2x plus 10. Right? So now we're up to 2x plus 10. Now we're going to divide by 2. 2x plus 10 divided by 2. This 2 divided by 2 and just become x. 10 divides by 2 and becomes 5. And then for our last step, we're going to subtract our original number. So it's x plus 5 minus x, right? Because no matter what our original number was, we can keep using this x for it. And x plus 5 minus x is just going to be 5. So now we have proved deductively or algebraically that no matter what you put in from the start, your answer is going to be 5, right? And that's kind of how these like math tricks always work. It's not a trick. It's not a trick if near the end they say, oh, subtract the first number you put in. Well, of course it's going to work out the same every time. If you have someone add in a number and subtract that same number at a different point, obviously that's going to cancel itself out, right? But that is basically, that's really just a quick breakdown of what Math 2101A Unit 1 is going to be about. Right? And remember this stuff, the deductive reasoning, this is really the meat of the course. It's what it gets onto later. It's conjecture, counterexample, and inductive reasoning. That is indeed just as easy as it appears when you first see it. Right? And that going to be it. That's it. That's it, Twitch chat. We're done. Done-a-reno. That is going to be the final stream for the summer here at twitch.tv/NLMathman. It's going to be it, right? Yeah, well, maybe, I don't know, maybe I'll be back and make a few highlights or something like that, just to leave some stuff here in the stream for people who wanna who pop in and want to take a look or want to see what I have done with my past 63 working days. A bit more than that actually, because I had a week beforehand getting this ready, so it's more like my past 68 working days. I did want to say before I go, right? I did want to mention social distancing and COVID-19 again, because of course that's the reason why we're here. That's the reason for the season, in a sense. The reason for season 1 of NL Mathman's Math Help Stream, that season. It's the reason for that one. And yeah, I am, like I said in the email that I sent out earlier today, I'm very proud of the effort that this class has put in. Very proud of the effort that the province has put in too, of course. But I mean, obviously, I'm talking to a small subset of the province here, right? But it is amazing to see that that Newfoundland has had 0 cases in COVID-19 for so long. I mean, it was a bit touch and go there, right at the start with the calls cluster. People, it was a bit concerning, maybe at the start. But I think and people came together and really took the advice of public health authorities to heart. And I think that people have done a really good job carrying on with the small steps that we can do to keep us and our vulnerable populations safe from a virus like COVID-19. I do want to say, just like it does, I don't really want to say keep our vulnerable population safe, because I think that sometimes leads to the wrong idea. Everybody is a vulnerable population to COVID-19. Some more than others, of course, but just because you're young and healthy does not mean you're immune to the disease by any stretch of the imagination, right? So everybody does need to be careful, especially now. If you're watching the news much, if you're following, if you look at a site like World Meter or something like that, or are following any sort of news releases, you may know that around the world, coronavirus cases are increasing faster than ever, right? Which is a very sobering thought. I don't want to be too negative here on the end of my stream, but they are increasing around the world. They aren't increasing here, at least not in our own neck of the woods. We are, of course, opening up the Atlantic provinces to the Atlantic bubble, right? So the 4 Atlantic provinces will now have sort of free travel amongst ourselves, which is nice to see. They're our neighbors and our family, our good friends, of course, the Atlantic provinces. So it's good to come together and allow some movement between them. You're at increased risk, Claire Darth? Yeah, plenty of people are. Plenty of people have increased risk from various other conditions that they have. Come from an ethnic minority group. Yeah, I mean, ethnic in the States, you might have seen statistics that ethnic minorities are at a significant increased risk. We don't entirely know why, but perhaps it is partly to do with sort of systemic societal problems to do with like access to healthcare and things like that. Would like to think that Canada does a bit better, at least for access to healthcare, seeing we have socialized healthcare as opposed to the States. But yes, there are very, very, very many factors that cause people to have increased risk for COVID-19. Colleague of mine, of course, has not of course, but a colleague of mine has. Don't like how they're trying to suggest the virus is discriminating against those from BAME communities. I don't know. I'm not familiar with that acronym. Does that mean like is that minority communities? Yeah, I mean, I don't think it's I don't think the virus. I mean, occasionally there are viruses with racially linked components, of course, or diseases like I mean sickle cell anemia and stuff, right? But yes, there are very many factors, and I do think that perhaps societal factors and histories of inequality amongst certain communities are and social economic status is perhaps access to the healthcare, lack of public health awareness. Yeah, absolutely. Those are incredibly important factors for the spread of COVID-19 and containing said spread. Of course, other conditions like other respiratory problems, like asthma problems and stuff like that, are obviously significantly increased risk as well. Um, I believe there's been shown some increased risk with heart conditions as well. A bit of a sobering thought for myself. Heart conditions do run in my family. Black, Asian, and minority ethnic. Oh, okay, okay. I believe in Canada too. There's evidence that Aboriginal communities are significantly more affected as well. But I would understand this. A minority ethnic would encompass all those visible minorities. South Central Asians, for instance, are at increased risk of developing diabetes and heart conditions, from what you have read. Yeah, I mean that's yeah, absolutely, it's entirely possible for sure, right? I mean, there's genetic components of various of many conditions, right? Um, yeah, what was I saying? Right about yeah, Canada, Eastern Canada specifically, but Canada in general, we are doing better than before. For example, I think countrywide, even Ontario and Quebec are doing quite a lot better. It is quite pleasant to see Premier Doug Ford even. I don't want to say even as if I underestimated the man, but he is very clearly coming out and saying that he will do what it takes to keep Canadians safe. Um, so it's good to see that the premiers and the prime minister, like the federal and provincial governments, are all on board with doing what it takes to keep people safe. So I feel very fortunate, very lucky to be living in Canada at a time like this. But that said, like we can't become complacent by any means. COVID-19 is still a very real threat around the world, and the numbers worldwide are increasing faster than before, which is, I mean, it's a scary thought, but it's something that we have to face. We have to look it square in the eye, right, to be able to combat it and to understand our own parts. Yeah, there's a like Slayer Darth, yeah, so many issues. Absolutely, there's a legion of issues, reasons for why the disease is continuing to exist and to multiply in the way that it is, and through the areas and the demographics that it is. And to receive many teaching accolades for your streams. Well, thank you very much. Thank you very much. I'm glad to hear that. And we may yet be back. May yet be back with more streams. But the thing is, right? Like I said very early on in these streams, I think it might have been on day like 5 on the stream, the end of day 5 when we talked about it. There's not a ton that any individual person can do to prevent the spread of COVID-19, but there is something that everybody can do. I understand that now if you're in Newfoundland or if you're in PEI or a place like New Brunswick and Nova Scotia where you have either zero active cases or almost zero active cases, or if you're in, I don't know, New Zealand or Australia or some other of the fortunate countries that have, the ability to close their borders or to restrict their borders more severely because they're islands, you may be lulled into sort of a false sense of security, right? But we do need to still be vigilant, to still realize that it is out there in the world and it is still a very real, persistent threat. Until such time as there is a widespread vaccine, it will still be a persistent threat that we need to be aware of. Not that you need to live every moment of your life in fear of it, of course, but just like wearing seatbelts in a car, right? I don't wear a seatbelt because I'm actively afraid of a crash at all points in time, but I'm aware that a crash can happen, so I keep myself prepared for it, right? The same with social distancing, the same with mask wearing if you're in public, in you know, like I said, in places with literally zero active cases. I don't know, maybe people don't always wear masks. I don't know, but in places where there is active spread, it's incredibly effective and incredibly important to to be continuing social distancing, continuing mask wearing, because PPE and behavioral practices are all we have right now. We don't have drug treatments, we don't have vaccines yet. They will come in time, but as of now, as of end of June 2020, we haven't got that yet. But we can still do our part. I also think that math is relatively easy to teach online remotely. The STEM subjects involving practical components are probably not going to be as easy to deliver remotely. Yes, there is truth to that. Labs especially, are exceedingly difficult. There are ways to do some online labs, but say you were trying to do a titration or something like that, right? A chemistry, you can't really. It's exceedingly difficult to do that. Math, like with a pen and paper example, like I have here, for sure, that is an easier one to do online. Something like English or social studies or things like that. Humanities, you can still have your verbal discussions and your essays and stuff can be done online as well. Um, yeah, there are types of teaching that will require some amount of on-site. Like the company I work for, the college I work for, does skilled trades as well, right? And I know that skilled trades education is going to be quite um, a lot more difficult to do via distance. I mean, I assume they would have to have uh, sections where people can come on site to do certain like practical and evaluations, but just have them be fewer students there at once, maybe more distance between the students and the instructors. Then we have a distance learning university in the UK uses remote controlled robotics to allow students use their STEM labs. That's cool. They're still not going to have experience of physically conducting the environments. No, absolutely they're not. And in those cases, it is, boy, just to have the infrastructure to have robotics for all students like that would be extremely difficult. Maybe we could use like Kerbal Space Program or something. That'd be kick-ass, right? Like a video game like Kerbal Space Program or Scrap Mechanic. Have you seen that? Scrap Mechanic to do some physics stuff. That'd be fun. But of course, then right, it ultimately breaks down to the difficulties of the program. But maybe every program will end up being taught like flight training, right? Where you end up with simulators for a lot of it. Hey, maybe game designers need to get on that. We need to get some simulators where you can do like accurate chemistry titrations and like first year physics labs and biology labs in a in a video game environment. Or like a trauma surgeon, but for, I mean, obviously not like actual trauma surgeon because that was a bit of a mean game, but trauma center. I mean, but where you could like dissect your frogs on there, you wouldn't have guilt in various other viruses like those anime viruses, right? That'd be a bit weird. but but I mean, video games and the ilk of like simulations. Hey, that could be a way forward for some types of education too, right? But it's getting a bit difficult and impractical at that point, right? Because it's going to take ages to develop such software, right? But yes, expanding and continuing distance teaching is of course a extremely important topic right now. It's something that I have put a lot of thought into it, and I would like to, you know, be able to put some more work into that sort of a field. But as time goes on, I gather there is some inertia right now in getting started. Of course, universities and colleges and schools and stuff. You can't just mobilize people to do those kind of things immediately, but it is a very real, um, it's a very real thing that needs to be mobilized, right? Manpower and um, I shouldn't say manpower, it's a bit sexist. Human resources, I mean human power, I guess, right? Human resources needs to needs to be mobilized to solve these sort of new issues of education in 2020. But anyway, yeah, I think I'm gonna wrap it up here for a bit. This will be yeah, this will be my break now, I suppose. After several months here now of distance teaching, we're going to take a bit of time off. Maybe we'll be back for season 2. Maybe back in September. Maybe even back before that. I don't know. We'll see how things go down. But probably if NL Math Man's going to return to the same math time and the same math channel, it'll be after Labor Day in the fall. Right? Thanks for being here, Slayer Darth especially. Yeah, you doing yeah, chiming in chat and keeping me company for a lot of these. It's good to have a virtual TA to help with the subjects, and very happy to be teaching anyone who wants to learn from what I'm yammering on about here on stream. But yes, thanks very much for being here with me. I am going to go now. I do have to go relatively quickly here because I have a fair bit of paperwork to get done before my colleagues end their day in about 2.5 hours or so. Right, I got stuff I got to send off and gotta scan in. Fun with your off time. Looking forward to hopefully catching you back in September. Yes. I would look forward to that very much. Hope you'd be back here then. Yeah, have a great summer as well. Hope you carry on with your education. Well, you're very welcome for all the teaching. I'm glad to be here helping. Glad to be helping things feel a bit more normal in this very abnormal time, right? But we're making do, we're adapting and carrying on, and that's the best that we can do, right? Thanks for being here, and like I would say before, I'm pulling for you. right? Because we're all in this together. And keep your stick on the ice, as the immortal Red Green has told us, right? Thanks. Stay safe out there, and I'll see you again in September.